Okay, good morning. Can anyone hear my voice?
เย็นอาจารย์
Thank you. Okay, so I think we are ready for the last discussion. And before we start the discussion on the examination, I think it's better to provide you a little bit on the MATLAB applications, which I think I already shared this information with you before in the handout, the file that I have shared with you before. Just if I understand correctly, okay, maybe this one. I think this is okay. This is the last chapter, right? We already discussed about this and discussed about the convolution integral, which is not so practical when we are trying to implement in the computer programs, do the algorithms. Even with the Excel file, it's not so effective or efficient for the computations of the dynamic system. We found another way of thinking is much better. You will learn with Dr. Chatpan maybe, which they use the direct integrations. They try to solve our system by assuming something. And I think it is more practical when some engineers, they look at the system and say, if the time delta t in this picture is delta tau, it's very small. They say that they could assume that the acceleration of our system is constant, or the accelerations of our structure is change in the linear behavior. Such kind of assumption can be effectively implemented and found the application of the direct integrations is much more efficient. And I believe that Dr. Chatpan will discuss with you in the second part. However, there is another way of thinking, solving this system, I mean the dynamic system. Many mechanical engineers, many aeronautic engineers, I think, they found something is more efficient. They say that the way they solve the system, the structure, for example, mechanical engineers, they would like to solve, to get to know the vibration of the car or the vehicle when they travel with the different speed on the different kind of surface roughness or the load roughness, the irregularities of the street, of the road, of the highway. They want to design the vehicle, right, to efficiently have a very small vibrations to get the driver or the passenger to have a very comfortable in the car. The way they solve, they don't use the same thing with the civil engineering applications. They use the what they call the state space technique, which I believe that I have discussed with you before in the applied mathematics, right? And maybe this one. Oh, I'm sorry, I cannot write down anything today since I have to use a MATLAB and I switch from the Surface, the tablet to my laptop, which is quite difficult to write anything. However, I think it's not so difficult for you to follow up, which when I say the state space, I mean this. You can find in the textbook this one, right? This file by Professor Gary Hart and Professor Kevin Wong. The idea is that the same thing with the MATLAB implemented. We try to solve the second order differential equations, and to solve that second order differential equations, they transfer or they transform the second order differential equation into an equivalent first order differential equations. Okay, so you see this is a single degree freedom system here in 2.177. And this is single degree freedom system. To solve this second order differential equation, they proposed the new variable called the z. Z is a new vector contain x and x dot as in 2.179. Okay, and then you obtain this second order differential equation, we change to the equivalent first order. It's this first order because this is a c dot, only one derivative on the new vector z, and on the right hand side in this term you have a coefficient matrix here, right? Multiply with the z of time t and the force function as in 2.179. To solve this one and this internal matrix, you can have something like this. To solve this one, the idea is very simple. This is the what they call the space equations already. And to solve that one, they use this term, I think. They do the integrations as in equation 2.1x4, in which the effect of the initial condition z0. Let me make it more bigger. Okay. This is the initial conditions contained in the vector z0. You have the x dot 0 and the x 0. That is the initial velocity of your system and the initial displacement of the system. They multiply with the e to the power at. This is quite new to you, I believe. Okay, but if you look at the applied mathematics, this one is called the transition matrix. The exponential of a diagonal, a matrix multiplied with any time t like this, right? Because it's a transition matrix. And then plus the term of contain the effect of the force. These two terms. The term contain the effect of initial conditions and of the force. And if I implement this one in the computer programs, I can assume that the force Fs of mine could be very small if I perform the integration. I will assume something like if the delta S is very small, the time step is very small, the force F can treat as a constant function or just a constant quantity. So it's quite easy to perform the integration of this transition matrix only, even though the force is arbitrary. But when you perform the integrations, you can consider piecewise, you can consider each delta t of the effect of the force. So it can assume to be a constant force during the very small time delta t like that. Okay. Let me find a way. Okay. This is the way they compute the transition matrix. Let you, okay, maybe this one. I have to, if you want to compute the e to the power at, what you have to do is to get the, what they call the eigenvalue and eigenvector of the matrix A, and the eigenvector in this textbook is a T matrix, a big T. This is a eigenvector, and the lambda here, maybe there as well, is the matrix of the eigenvectors of a matrix A. Okay, and in the MATLAB there is a function to get this, the transition matrix. Very simple. I think I will show you later, but if you want to have a good background or the theoretical background of this state space, please come to visit to understand through this part of the textbook. It could be very helpful. Okay, this one is a new math beta. This is another idea that Dr. Chatpan maybe will discuss with you. So I skip. Okay. It seems only the state space that I will show you today. Maybe should be. I want to find the iterations equation. Where's the iterations? Let me do this for you. Not so sure whether we have, okay, maybe here. No, it's still the integrations. Okay, this one. The difficulty when we implement these algorithms, this equation into the computer is that if you want to compute it at the time t, any time t, it could be better to go stepwise. You go step by step. You go starting from time 0 and go to time t equal to delta t. Go to time t equal to 2 of delta t. Step 3 is 3 delta t. Step 4 is 4 multiplied with delta t, something like that. And the efficiency of the computations will come if I can make use of the previous information. For example, to compute step number 4, if I can use the result from step number 3, it could be very helpful, right? It can help me to shorten the time, computational time that I will need to compute everything, because only small information I need, additional information I require. Okay, so this is called the not recursive, right? You do the computation that what they call the recursive computations. You go stepwise, step by step, and the next step is come from the present step, something like this. The computation is very efficient. That's why we need to change the integration form from the previous equation. I forgot, it's 2.100 something, right? And now you see, this is a step k plus 1. The step k plus 1 can be computed from the step k. Step k is here, right? Started from the very beginning of this equation, step k. This is the thing like a initial state of the k plus 1. The initial state for the zk plus 1 is come from the zk. So the vibration at this present time will be used as the initial condition for the next step of computation. Something is like that, right? And this is a multiplied with only delta t. One step ahead. So this is the effect. Can you still hear me?
Yes, Ajahn.
Okay.
Yes, Ajahn.
Okay, thanks. But you see on the second term on the right-hand side, you deal with the integrations. But this integration is the effect of the force at the time step k that will affect the vibration on step k plus 1. This is the next step, right? The future step. And these integrations, we consider this effect is only from tk to tk plus 1. So if you can control the delta t or the time step or step size to be quite small value, then your F, your force, can be treated as a constant force. That's why they put only the force evaluated at the time step k be a fixed number, a constant. It's not a time function. So to get the integration of this, it look like you perform the integration of this term only. And the integration of this term become the second term here. And in the reduced form, a compact form, it's become the A inverse multiplied with the e to the power at. This is a transition matrix minus I, and then multiply with the F. Okay. So I would say this one, the first transition matrix. Okay. And the second one is the effect of the force coefficient matrix. The transition matrix will multiply with this state, present state, or the condition of your structure. What is your velocity or what is your displacement at this time equal to t? And if you tell me about that information, I will multiply with the transition matrix e to the power a delta t. I can predict your effect of this initial condition for the future. That will be estimate of the displacement or the velocity of the system in the next step or in the future step due to the effect of the initial conditions. Okay. And the second term, if you tell me about the force, now the force is equal to Fk, and I would like to estimate what would be the vibrations of my system in the next step or in the future, and that future is just the delta t ahead. It can be computed from just that amount of force multiplied with this coefficient matrix, okay, of the second term. That's it. So to implement this computation is very, very efficient. I would say that, and I think I can perform that in the MATLAB for you. Let's see. This is what. This is another file in the handout folder, and you can find the MATLAB script and try to solve the 2D gear freedom system. This 2 degree freedom system is the system that contains the mass M1 and M2. Previously, we considered only the first order, I think it's a single degree freedom system, right? But this example is a 2 degree freedom system. I will try to use my mouse to draw for you, but it's not so good, I believe. It's quite difficult for me to use a laptop to do this job, but I try to. And you can imagine you have the spring. And you can imagine you can have the dashboard. Okay, connected to the mast. And this is already a single degree freedom system. But in this example, you have another mast connected together. It is. Okay, sorry, maybe it's not so, it's not look good, but I think it could be helpful for some of you to understand about what's going on here. You have the mass M1 and M2, right? And this is X1 and this is X2, I think. Okay. This is degree freedom 1 and degree freedom number 2. Okay. So the M1 is the mass of the first degree freedom. Is a kind of 471. The unit, maybe you can thinking about kilograms for the mass. The stiffness spin coefficient of the K number 1 is 1,400 something, right? The unit you can imagine something like a Newton per meter. And the damping coefficient C is 33.5. The mass of number 2 is much smaller. It's just like, I don't know, less than is 10, 1, it could be 3%, right? About 3% of the mass of M1. And then you have the stiffness of this amount, the damping of that amount. And I just provide you the note showing that you have the frequency, the damping like this, like that for each degree freedom system. Then I construct the mass matrix, the C matrix and the K matrix. Okay. And this is the way that we believe that you have when the force acting on the mass M1 and M2 it could be something like this, B1, B2. You can imagine you have the force. The blue color is the force acting on the mass. F1 and F2 is like this, right? So this is equation of motion. You can write down the equation of motion as the mx double dot. You contain x1 and x2 inside. Cx dot and kx. And remember, x is not only 1x. Now it's contain x1 and x2 in the vector. And the bf is a coefficient of the force, I believe. Let me write down for you the equation of motion. Otherwise, you might not. M to be m x double dot. I'm sorry, the dot is very small, right? Plus C x dot. X dot plus kx equal to BF B, the subscript is F, and multiply with 0, 1. It could be any force function ft. Then in this case, it looks like I provide the force function f. Oh, let me do. And this force function f, it could be something like a sine function, cosine function, depending on what you want to do as the external force. And the BF is just coefficient, right? When it says 0 and 1, it means the force only at the degree of freedom number 2 will be applied to the system, since I put 0 on the first degree of freedom. But if you want to apply this force function f of time t to both degree of freedom, you need to let this one equal to 1 and 1, right? Unless you know that the amount of the force in the degree freedom 1 and degree freedom number 2 is like a 2 and 1, 3 and 1 is a 3 times or 2 times to each other, you can provide something like that. But the two force in this example is controlled by the force function F. If you want the force at the degree of freedom F1 and F2 to be different function, you can just put BF equal to the force F1, and this is F2, okay? And F1 and F2 defined as the different function, independent function. It's up to you. Yep. In this example, let me do like this for simplicity. Then I do the inverse of the mass. And this is the A matrix, right? When you write down the state space, it's something like this, right? I'm sorry. You can think about the state space in which if I write down the new variable C dot, it could be something like this. And the Z is contained inside is what? Is the X and X dot, right? This one, I believe you can remember, is called M inverse. M inverse, and then matrix C, something like this. And another, let me go back a little bit to the, when we do the equations of motion, okay, you can have this. You know that it's going to be something like A equal to, but in my case, I use the velocity and the displacement. But in this example, they use a displacement vector follow with the velocity vector. So they become a little bit different, right? In my case, I use X dot first and come after with the X function, X vector. So the matrix here could be the minus M inverse C here. And I would get I there, and I would get at this one is 0, and at this one could be something like minus M inverse K, right? So the position of the element of the matrix A could be different from this textbook and my example. Sorry, it could be M inverse C, M inverse K, the I is I, this one is I, and 0. Okay. And then this one. This is a state space. When I tell the MATLAB about the delta t. Then use this function c to d. But remember, if you want to use this function c to d in your MATLAB program, you need to have what they call the signal processing toolbox. Without the installation of the signal processing toolbox, you cannot have this function c to d. Okay, I call the function c to d. This comes from continuous to discrete. I want to convert the continuous model to the discrete model. I provide the A matrix, I provide the B matrix, here A and this B, right? And delta t to them, to this function. And this function will return me the another two matrix. This two matrix is a transition matrix, AD, and the coefficient force matrix, BD. What is AD and BD? Let me go back here. Okay, once you have a matrix there like this, and this one I can remove the matrix outside and multiply with the zero and the force function, f, small f. Then the coefficient in front is just the BF, the B matrix of mine. And then you see, to solve this equation, I need this one is a transition matrix. And now it will be the matrix A sub D. And this one is gonna be B sub D of mine. Okay. A discrete and B discrete. So I have this, AD and BD. I will solve from time from 0 to 50 seconds and assume that the initial conditions of my building is 0, 0, 0, 0. No initial conditions, right? And this is just the vector that I want to install the result. Okay, this is the force vector. My force, the F, my force is a psi function. So it looks like I apply the force as the 2 pi 0.28 t. The frequency is 2.8 hertz on the building, but at only the second degree of freedom only. Remember that, right? Since coming back to here, since the BF, you see, we put 1 only at the second degree of freedom. And then this is just, you see, the multiplications. To get the solution is very simple. I put the AD multiplied with the X and BD multiplied with the F. At A, this is a time loop, while loop. And in each loop, the time t is defined, and the delta t is very small, right? Defined as 0.01 there. So I will compute at each step of time, starting from time equal to 0 and increase 0.01 at each step. And then I compute the force, the present force, and predict the future one step more ahead by using this equation. After I got and obtained the X, I will use X to augment it into the total solution XX. And this is about the force. I mean, I will store the X and I will store the output of the force and the time t like this. And then you see I increase the time to the next step by t equal to t plus delta t. And then I will go with this loop until the t equal to tf. And then my computation will get out from the while loop like this. And I plot for you, I think, the force function, the loop, and the force displacement. So this is the main computation. This is this equation. X equal to AD multiplied with X, okay, and BD multiplied with F. At each step, the X will be the present information about the X, right? Will be put here, and then I will replace by the new X for the next step. And I will store X there. Okay, like this, keep like this. And this equation is exactly the same equation as this equation. ZK plus 1 equal to AD multiplied with the X plus the b sub d multiplied with the f. Exactly the same equations. Let me do for you in the MATLAB very short time, I think. Let me start the MATLAB first. I have to test the program. Okay. It will take a few seconds to load the MATLAB program. Sorry for the time. Okay. Let me see the version I have. Okay. Signal processing. Okay, this one. You need this. If you want to call the function C2D, you need this signal processing toolbox. Okay. Okay. When I do like this, it means I have it's a convert continuous time dynamic system to the discrete time. It's very simple. It's already built in the MATLAB program already. So let me do the script for you. Try the new one. Can you see my screen? You can now see the MATLAB, right?
Yeah, Ajahn, I see.
Okay, now I change to the PDF file that we discussed before. This is a script of my file. Let me do the copy for you and put it on the script. Remove the comment. Okay, put the first function, the loop displacement, the first floor displacement. Okay, this one we also to be okay. Okay, I have to save first, I think. I just test number 1. Why don't I do with the test number 2? Oh, sorry. It's number 2. Okay, the file is called test02, right? Then I just click on this test02, press enter. Now you obtain the result. You see this? This is the first function I apply. It's a sine function. The frequency is, as you know, 0.28. This one is the frequency of the first. Okay, and the result show the loop displacement and the first floor. We have only 2 floors now. The first floor and the loop displacement. I'm sorry that the scale is not the same. The loop displacement is at 0.1. What is the peak? It's over there maybe. It's about 0.07. Maybe you're thinking about 7 centimeter maximum, and the displacement of the first floor maybe here is okay at the time equal to 24 seconds, but the displacement of the first floor is only 1.9. It's about 2 centimeter maximum. Okay, something like this. If you want to test the free vibration for you, it's very simple. If you have this type of the code, for example, if I want to, it could be the displacement could be there. Let me do the displacement of the loop is the last one is a loop. The second, if I move the loop 1 meter here, and I want to see what gonna be the what the free vibration of the system, of these two vibration system, and let the force equal to 0. So I put multiply with 0. Okay, so it's no force acting on this building at all. Only the initial displacement of the loop equal to 1 meter would be applied, and I would like to see what's gonna happen. Then you got the save, and then I run the script for you. Yeah, it's changed to this one, right? See the force function, it kept 0 all the time. But you have the loop displacement starting from 1, the unit meter, for example, and you see it's gonna be the free vibration. This is gonna be the free vibration. But the free vibration is not so beautiful as the single degree freedom system, because right now you have the 2 degree freedom system. I let the loop go 1 unit or 1 meter, but the first floor I fix to 0, right? And once I release, the building will keep shaking, or vibration is occur in this 2 degree freedom, and the vibration is like this. Even though it's free vibration, but the curve is not so beautiful as a single degree freedom system that you can expect the pure sine or cosine function multiplied with the exponential of time. But this one is a little bit more complicated, right? It's come from 1, go to 0, and then it'll increase a little bit and then go to 0 again, something like this. Okay. And if you want to change the frequency of the force, what I have to do, let me change the initial condition back to the 0 again. And if I try to apply the force, 0.28. If I change the frequency to maybe 10 times, let me try with the 0.2.8, something like this. It's very high frequency, 10 times higher than before. Let me save and execute the script again. You see, now the force, even though the amplitude is the same, let's assume the amplitude of the force is 1 Newton. I apply the same amount of force to the building, but you see the displacement now at the loop is 10 power minus 3. It's a 10 power minus 4 at the first floor. So this displacement of the building gonna be very, very small. As we have learned in the force vibration in the chapter, I don't know, number 4 maybe, about the harmonic force vibration. If your beta, the frequency ratio is very high, you can expect the DAF gonna be close to 0, right? Very small too. That's why you see, I cannot induce the vibration of the building if the frequency, exciting frequency is rather high compared with the natural frequency of the system or the building itself. And even though this one, you have 2 degree freedoms, but they follow the same rule. Okay, the behavior of the multi-degree freedom system gonna be explained and discussed with you again with by Dr. Chatpan. So I skip this part. Okay, that's gonna be all of what the information of the first part that I would like to discuss with all of you. Okay, so I would like to end my discussion of the first part here, and hope this information would be helpful to some of you or all of you who would like to study about the dynamics and vibrations of the structures. Okay, this is a time for the questions. If you have any questions, please.
Ajahn,
Yeah.
in the exam, is the closed books or open book, Ajahn?
Oh, in the exam, right? I will discuss about the exam with you. If you don't have any question on the issue we discussed so far, why don't you start with the previous exam first? and then where I will explain to you about what I expect to have in the exam this year, and then you're welcome to ask me again about the exam. Okay. Let me try to stop this one first. Close the MATLAB. Okay, I have this file for you, right? This is a previous exam. The exam will take like 3 hours, right? And we already made an appointment on the March 2nd, am I correct? In the afternoon, starting from 1 o'clock till 4 o'clock. Am I correct, everybody? Right? March the 2nd, okay? If you don't have any comment on that, I assume that all of you realize about that already. And in the exam, I will have the question, how many? 3 maybe? Yes, I have already 3 questions that year. And in this year, I will do rather the same. So you can expect about the same amount of questions to ask you in the exam on this coming March. And I think the first question is a question about free vibrations. This is about free vibrations, where I ask my student to calculate, what is that? For example, number 1 is decide the maximum cable length of the bungee jumping system that can be installed on the bridge, which is 100 above the river. Okay, it looks like they call the bungee jump, right? And the jumper is standing on the bridge, and then they had the rope or cable, which have a rather high elasticity and the strength to carry their body. Once they jumped to the river, we expect that maybe the hand finger can touch the water in the river, but it's not the body. Okay, so we have to decide what's gonna be the length of the cable like this, in which the requirement is to guarantee that the body of the jumper with a height of 2 meters and the weight of 200 kilograms shall not touch the water. Okay, so the target is very clear. After you jumping from the bridge, and your mass will come down to the river according to the Earth gravity. Okay, the speed is starting from 0 for sure, and then you have the speed faster and faster and faster during the falling down of your body. And once the cable, if its length is out, come to straight, then it's gonna be active. The cable will try to acting as the spring and bring your body back to the 0 position, right? So the question is a kind of you have to compute the initial velocity and the displacement where the cable will active, so that I can stop you before you touch the lever. Before your body touch the lever, if we assume that the height of this guy that we use for the design is 2 meters tall, okay, something like this. So you have to write down the equations of motion. You have to compute the initial velocity due to the gravity of the Earth. You have to write down what's gonna be the length, maximum length of the cable, which we need to provide Okay, given you the properties like this, right? The cable cross-section areas, the modulus of elasticity, and the damping ratio of the whole system. Okay, like that equation, calculate the traveling time. Okay, and also I asked you about the traveling time before the body start to rebound, or the body rebound. Assume that the waves. Okay, something like this. I don't want to go in more detail. Let you try to solve or consider this question yourself. Okay, but how difficulty and how I ask my student is something like this. My point is, I want to how to say, let you try to apply the knowledge of the dynamics of the chapter 2, chapter 3, right, free vibration, to the real life. And this is one of example I can think about when we do the bungee jump. And with the knowledge of the free vibration, I believe everybody of you can do this job. Okay. The second, is the beam which is installed in the pendulum machine having the mass m at the midspan as shown. Please answer the following questions if the pendulum mass m is forced to rotate counterclockwise with a constant rotation velocity v with the arm length r. It should be noted that the gravity effect of the horizontal vibration can be omitted. Okay, you can neglect the effect of the gravity. Okay, so the beam is at the starting point is assumed to be no deflection at all, right? Because we don't care about the gravity of the earth. Then the mass is attached on the midspan and it's assumed that the beam is massless, have the property of EIL and damping. And then the small mass m is fixed to the big mass, big M, and it's keep rotate counterclockwise. So you can imagine that it's gonna be the vertical component of the force. It's a kind of the centrifugal. You know about this one, right? It's the force is M multiplied with the V square over R, something like this. Okay, this is a centrifugal force, and I provide you also the information of this physics. And from this, I ask you to write down the equation of motion, focusing on only the vertical degree freedoms. So I expect this is the single degree freedom system, okay? Because even though you have the two mass, the small mass M and the big mass M, but you have to cut at this point, cut the rigid arm of the pendulum here so that you can replace it by the external force. And that external force have to write down according to the centrifugal force theorem, like this, okay? So it's gonna be something like the external force acting on the big mass M, okay? And you write down the equation of motion, including the external force on the right-hand side. And this equation is equation of chapter, what? Chapter 4. It's about the harmonic force vibrations, okay? Once you write down the equations of motion clearly at the midspan, you can determine the maximum steady state deflection under any constant rotation velocity. So what I have to ask you is about the cross-form solution. I want from you is to obtain the cross-form solution based on any constant rotational velocity of the pendulum. I would like to get the maximum steady state deflection. Okay, so you have to solve the equation of motion and get the steady state response and find the amplitude. Okay, find the amplitude of that steady state response or the deflection. as a function of constant rotational velocity. That's it. Okay, that's it about the 2.2. Then the 2.3, find the velocity v of the pendulum that can induce the last scale deflection, considering only the steady state response. Okay, I believe from 2.2, you already have the closed form solution, so it's quite simple for you to consider your solution from 2.2, where or when of the pendulum velocity that will produce the maximum deflection, the last scale deflection of the beam, if the speed or the velocity of the pendulum is bound with the range of 0 to 25 meters per second only. Okay, so that's not so difficult. Let you do this job yourself, try to solve that one. And this one, number 3. Number 3 is quite straightforward. I think I only provide you one example of the single degree freedom system subjected to the periodic force vibration like this. So this one is gonna be chapter 5, maybe. Okay, in which the force F of time t is a kind of a triangular function, periodic functions. So what you have to do is very straightforward. You have to convert this force function F of time t replaced by the Fourier series, right? You need the sine and cosine series to help you to transfer or transform this force function to then equivalent. Another force function is a combination of sine and cosine. Using that Fourier series, you end up with the summation of the force component of many sines and cosine terms. And then you just apply the harmonic force vibration knowledge to compute the response of your building. Okay, and I expect that there could be one point here is the truncation assumption. I would like to get from you your answer that when you will stop your computation, since the force function, even though you convert to the Fourier series, is contain infinity terms. It's contain term from n to infinity. Then I would like to see from your answer what would be the good assumption for the engineer like us to stop our computation when the frequency is quite high compared with the natural frequency of the building. Okay, you consider on the effect of what they call the beta parameter. Look at beta parameters, the frequency ratio beta. You can say something about the truncations, and then let you compute only the first few terms and obtain the total solution. That is what I expect to get from my student from question number 3. And that is could be all, right? Okay, that could be everything from my side. Now is the question. Please ask me again if you have the question on this topic, including the exam as well. Please, if you have any questions.
Ajahn,
Yeah.
can I ask you about a sample for Fourier series?
Fourier series, why not?
Yeah.
Okay.
Example.
Example, the Fourier series, what you're talking about here, maybe. I don't know. Let me find for you. This one?
Yes, right. Okay.
Okay.
On 2 page.
Page number 2?
Page number 2.
Where is it?
What's mean of phi 1c and phi 1s?
Oh, you're talking about the
Meaning
subscript here?
subscript, yes.
Okay. Maybe number one, I would like to refer to the component one, right? Like the big omega one. Remember your force. The force function is contain many frequency. In this case, you have the 2 pi and you have 4 pi, right? As the big omega. The big omega 1, I mean 2 pi. And big omega 2 here, I mean 4 pi. It's a different frequency. To obtain the response of this big omega 1 component, the term here, I believe, is come from this one, right? Is a cosine of 2 pi minus 1 phi 1c and phi 1s. And if I understand myself about the expression of this, I believe that c is come from cosine and s is come from sine function. Understand?
Okay, Professor. Thank you.
Okay, welcome. Any other questions if you have? Okay, if you don't have any question, I would like to suggest you something that since the exam will start on the 2nd of March, this is Wednesday of next week. Okay, allow me to start thinking about the exam on Sunday, 27. And once I start thinking about the questions of the exam, I would like not to discuss answer you any question. Otherwise, it's not fair. Maybe it's close to the question so much, and I don't want to provide some more information at that time. Let you be able to have a question with me until the Saturday 26th. Is that fine for all of you? In the live group, you can ask me anything about the exam, about the chapter 1 to chapter 7. Oh, but chapter 7 is about the general. Chapter 7 is not in the exam, okay? So chapter 6, what is chapter 6? Chapter 6 is a support motion, right? So you have chapter 1 to chapter 6 for the exam. I don't want to have chapter 7 in the exam because that one is just a computer. It's not test you the understanding so much. So please scope our exam by chapter 1 to chapter 6 only. Okay, so you can have any question to the live group. Please use the live group because I want to share with everybody my answer, your question, everything will share to everybody, right, in the group so that everyone will know what is the information. Okay. So hope you have a good preparation for the exam and see you on the exam date Wednesday next week. And we will do through the Zoom again. I will start the Zoom for you and let you have at least, I think, to have the camera turned on, okay? I will record this exam session for a review after. If someone say that it's not fair for this guy or this person, they use a computer, professor, please don't they allow to use. I will have the record of that, okay, to the Zoom recording. And it's an open book, but not allow you to use the MATLAB, okay? Just the calculator is allowed. And you can have the Google, you can have anything, it could be okay, it's fine for me. But don't use efficient computer programming or something like that to help you to solve the question. No question, right? Okay, so I would like to end my discussion for the first part here, and hope you wish you have a good day and good time preparing for the exam next week. Okay. Okay,
Ajahn,
thank you and have a good day. Goodbye.
Sorry, Ajahn.
I'm sorry.
We still have class on the third day or not, Ajahn?
No. You just have plenty of time for the midterm where you can have this time for preparing yourself. But you can
Yeah.
give me my question to the live group. That is what I allow until this coming Saturday, right? Okay.
Yes, thank you, Ajahn.
Yeah, you're welcome. Okay. Good day and goodbye.
Thank you. Ajahn.
You're welcome.
Thank you. Goodbye, Ajahn.
Goodbye.